Hello, and welcome to Business Calculus Continuity. Continuity is the property of a function that is unbroken. The graphs of continuous functions can be drawn without lifting your pen from your paper. This is a very simple idea, but it expresses itself in a number of important ways. So we're going to be going through several examples to show you where continuity applies, where continuity is broken, and how to analyze a graph and the equations of functions to determine these properties. We also say that a function is said to be continuous over an interval when there is a group of connected x values where the graph is unbroken. So let's look at some of these examples. Take, for instance, our first function, f of x. We want to look at the limit as x approaches 1 of this function. And we see that as I get closer to 1, in the x value, my function is getting closer and closer and closer to this point, which is 1, 3. We see that the limit as x approaches 1 of f of x equals 3, in addition to the fact that the function itself, evaluated at 1, is also equal to 3. We also want to look at this same limit of our next function, g of x, which is a little bit more complicated looking, but we see that the graph is very similar, except for one extremely important detail. The limit as x approaches 1 of g of x is equal to 3. As we see, I can approach it from either side, and my function values get closer and closer. However, you'll notice that down here we say that g of 1 does not exist. That is because there is a hole in the graph at x equals 1 because of our denominator, which doesn't allow us to plug 1 into the function because we would be dividing by 0. So in this case, the function fails to be continuous because I cannot draw the entire picture without lifting up my pen to skip that one point. Our final example here is h of x equals the absolute value of x divided by x. This is an example that we've seen a couple times before, and it shows us an example of a jump discontinuity. If I look at the limit as x approaches 0 from the left, we see that I'm approaching the value -1. But if I look at the limit as x approaches 0 from the right, we get an entirely different number, 1 instead, and there's this very large gap between those two values. Because the one-sided limits do not agree, we say that the limit as x approaches 0 of h of x does not exist, in addition to the fact that the function itself is not defined at that point because there are holes in both of these locations and no other blue dots that appear along the x-axis or the y-axis to indicate that there's some other value that the function obtains. Now that we've talked about continuity a little bit and shown you some examples, we want to put it on firm theoretical ground. We say that a function f is continuous at the point x equals c if the following three conditions are met. The limit as x approaches c of f of x exists, the function evaluated at c exists, and the limit as x approaches c of f of x equals the value of the function at c. So basically, if I'm approaching a particular value, I want the limit to equal the function. It's a very nice property to have. Furthermore, we say that a function is continuous on the open interval from a to b if every point in the interval ab is a point where the function is continuous. And we say that a function is discontinuous at a value x equals c whenever any of the three above conditions fail to be met. So, we're going to do a couple more examples. We would like to determine the continuity properties of a function defined by its graph. So here we have an image, and we're going to do a quick visual inspection and see that the trouble spots of the graph occur at the following values: -1, 0, and 1. And what we're going to do is take a closer look at these values. First, let's determine the continuity properties of the function at x equals -1. When we talk about the continuity properties, what we want to be looking at are our 4 behavioral indicators. We're going to look at the limit as x approaches -1 from the left of our function f of x. And drawing our arrow here, we see that the limit as approaches -1 from the left is approaching 1, so we'll make note of that. Okay. Next, we're going to be looking at the limit as x approaches 1 from the right, and we will use a different color to make this easier to see. Now up here, we see that the function is behaving a little bit differently, and we're approaching a different value. As we come to -1 from above, the limit is equal to 2. Now, we see that we have the left-hand limit and the right-hand limit not coming to the same value, so that tells us that the two-sided limit of f of x does not exist. And then lastly, what we would like to look at is the value of the function itself at -1. And if we look very closely, we see here that the value assumed by the function is equal to 1 at that point. So our limit does not exist, but our function is defined at this point. However, we must conclude that at -1, the function is not continuous. All right, let's look at our next value. We want to determine the continuity properties when x is equal to 0. So we start in the same place. We're going to look at the limit as x approaches 0 from the left and come in down this direction. We see that we're getting closer and closer to 0, and so we recognize that this is our left-handed limit. Next, we look at the limit from the right, and coming down, we see also again that our value is equal to 0 as we come down to 0 from the right. Because our one-sided limits agree, we do get to say that the limit as x approaches 0 of f of x is equal to 0. But, as we can see from the picture of our graph, this value here shows that the function is defined to be something other than 0 when x equals 0. Because the function's 1, these two values do not agree. So again, we must conclude that our function is not continuous when x equals 0. Let's look at one more value. We want to determine the continuity properties at x equals 1. We take the limit as x approaches 1 from the left of our function. We follow along up this way, and we see that the function is approaching the value 2. Next up, we look at the limit from the right. We come down on our function this way, and see that again, our function is going to be equal to 2. Because our two one-sided limits agree, we're allowed to say that our two-sided limit, the limit as x approaches 1 of f of x, is equal to 2. So our limit exists. However, we see that there are no values that the function assumes when x is equal to 1. So f of 1 does not exist. You can also say that f of 1 is undefined. Because this does not exist, one of our three conditions for continuity was not met, and we must conclude that also at x equals 1 that our function is not continuous.
All right, using what we know about graph and continuity properties based upon this graph, where is the function discontinuous? Is it when x equals negative 2 and 3, negative 2 and 2, 0 and 2, or none of these? Thank you very much for listening.